Now, good day. We'll discuss the illustration of limit theorems. So, in short, we'll be discussing the limit theorems. So, in lesson 1, we show that, or lesson 1 showed that the limits can be determined through either a table of values or based on the graph of a function. Now, must one always construct a table or graph the function to determine a limit? So, must we always do that? That we always do a table or make a table and provide a value of x from the left and from the right of your c, and also observe whether your f of x approaches a specific value, or you're just always graph your function. Now, we may use the limit theorems for us not to always construct a table or graph the function. So we have 8 theorems in general. So this will enable us to directly evaluate limits without need for a table or a graph. So in the following statements, C is constant, F and G are functions which may or may not have C in their domain. Okay. Now, number 1, the first theorem. The limit of a constant is itself. So when we say constant, so that is a number. Okay. So if k is any constant, then the limit of k as x approaches c is always the constant itself. So for example, if we have this limit of 2 as x approaches c, so this is equal to 2. The limit of negative 3.14 as x approaches c, and we have negative 3.14 still itself. If we have the limit of 789 as x approaches c, the result is 789. Okay, so if also we have this, the limit, okay, limit of 5 as x approaches 3, okay, based on this theorem, this is equal to 5. Okay, the limit of 300 as x approaches negative 1, this is equal to 300. Okay, if we will take the limit of a constant, if you take a limit of a constant, the result is always the constant itself. Okay, that is theorem number 1. Number 2, the limit of x as x approaches c is equal to c. So this may be thought of as a substitution law, but because x is simply substituted by c. Okay, so we have this. The limit of x as x approaches c is equal to c. So we have here example, limit of x as x approaches 9. So it is equal to 9. Limit of x as x approaches 0.005, it is equal to 0.005. Limit of x as x approaches to negative 10, which is equal to negative 10. So it's just like you're substituting the value of x or the value of c to your x. Okay, and take note, the form must be like this, the limit of x. Okay, no other number, no other variable, or no other term, only x. If you have the limit of x as x approaches c, then the result is c. Okay, that is the theorem number 2. Okay, for the next theorems, we will assume that the limits of f and g both exist as x approaches c, and that they are L and M respectively. So in other words, the limit of f is L, the limit of g is M as x approaches c. So let's go now to our third theorem, the constant multiple theorem. So this says that the limit of a multiple of a function is simply the multiple of the limit of the function. So when we have this multiple of a function, we expect that there is a constant. Okay, so we have this. The limit of a constant times f of x, meaning this is f of x is a multiple of k. Okay, a multiple of a function. So f of x is a multiple of k. So k times f of x. So if we have this, k is a constant, therefore we can just, maybe you can say that we can factor out or put k outside before the limit. So this is just like this. So we have now k times the limit of f of x. Okay, and based on our previous slide that the limit of f of x is L. So therefore the limit of k times f of x is equal to k times L. Okay, for example, take for example the limit of f of x is equal to 4 as x approaches c, for example. Then we have this, the limit of 8 times f of x. So meaning f of x is a multiple of 8. Okay, our k here is 8. Okay, so we can write 8 outside the limit. So factor out 8, or if you want to use that word, times the limit of f of x. Now the limit of f of x is given to be 4. So we have 8 times 4 is 32. Okay. Next example, we have the limit of negative 11 times f of x. So this constant can be written outside or before the limit. So multiply negative 11 times the limit of f of x, which is given by 4. So we have negative 44. So last example, if we have 3 halves times f of x, so the limit of this 3 halves times f of x, so we can write the 3 halves outside. So 3 halves times limit of f of x as x approaches c, which is equal to 4. So 3 halves times 4 is equal to 6. Okay, so this is the constant multiple theorem. So if you have a constant here, okay, the limit of a constant times a function, take note this is a constant times a function, you can just always put k before or multiply k or put k outside or factor out k. Okay, and then multiply it to the limit of f of x. So addition theorem. So if we have this, the addition of two functions, then of course it will be parang distribution. Okay, so the limit of the sum is equal to the sum of the limit. Okay, take note. Limit of the sum is equal to the sum of the limits. Okay, take note of that. So we have L plus M, and if it's minus, then of course L minus M. Okay, so for example, if the limit of f of x is 4, the limit of negative 5 of g of x is negative 5, then of course the limit of the sum is equal to the sum of the limits. So the sum of the limits, so we have 4, this is 4 plus negative 5 equals negative 1. And if it's minus, this is the limit of the subtraction or of the difference. The limit of the difference is equal to the difference of the limits. So the limit of f of x is 4. The other one, g of x, is negative 5. So 4 minus negative 5 is 4 plus 5, that is 9. Okay, take note of that. Okay, so theorem 5, the multiplication theorem. So this is similar to addition theorem with multiplication replacing addition as the operation. Thus, the limit of a product is equal to the product of the limits. Okay, this is the limit of the product, and this is equal to the product of the two limits. So limit of f of x is L and limit of g of x is M. So L times M. So again, let's consider the same limits. The limit of f of x is 4 and the limit of g of x is negative 5. So if we take this multiplication theorem, so we'll just multiply their specific limit. So the limit of the product of f of x times g of x is equal to the product of the limits. So take note, the limit of f of x is 4. The limit of g of x is 5. So 4 times negative 5 is negative 20. Okay, so say for example, if this is 10 and this is 30, so you'll just multiply 10 times 30 if this is the limit. No, the limit of the product is equal to the product of the limits. Okay, remark 1. The addition and multiplication theorems may be applied to sums, differences, and products of more than two functions. So therefore, we can extend this one. So we can have times g of x times p of x, okay, times q of x, and so on. So this will be times another limit times another limit. So it can be extended. The same with addition. So you may add plus p of x plus q of x. Okay, so plus another limit plus another limit. So this also, if you have another minus here, so the limit of this function minus minus. So it can be extended. So it may be applied to more than two functions. Remark 2, the constant multiple theorem is a special case of multiplication theorem. Indeed, in multiplication theorem, if the first function f of x is replaced by a constant k, the result is the constant multiple theorem. Now let's go to number 6, the division theorem. So we're done with addition, subtraction, multiplication, and now let's go to the division theorem. So this says this is the limit of the quotient. Now, if you look at this, the limit of the quotient is equal to the quotient of the limits. Okay, quotient of the limits. Take note of that. The limit of the quotient is always equal to the quotient of the limits. So say for example, again, we have these two limits based from our previous example. So the limit of the quotient is equal to the quotient of the limits. So limit of f of x is 4, limit of g of x is negative 5. Therefore, the answer is negative 4 over 5. Number 2, if we have 0, the limit of f of x is 0, the limit of g of x is negative 5. Therefore, taking the limit of this, the limit of f of x over g of x, so taking the limit of the quotient, this is equal to the quotient of the limits. So this is equal to the limit of f of x over the limit, okay, as x approaches c, and the other one is the limit of g of x as x approaches c. Okay, and limit of f of x is 0, and the limit of g of x is negative 5. So 0 divided by negative 5 is 0. Okay, last example, if the limit of f of x is 4 and the limit of g of x is 0, then if we follow this, now we have 4 over 0, right? We have 4 over 0, right? So limit of f of x divided by g of divided by g of x is equal to the limit of f of x or over the limit of g of x. So 4 over 0 is undefined. So we may say that the limit does not exist. Okay, again, if the denominator is 0, so it does not exist because it is undefined. Okay, second to the last theorem, the power theorem, meaning the exponent. So this theorem states that the limit of an integer power of a function is just the power of the limit of the function. So limit of the exponential function is equal to the exponential function or exponential of the limit, or exponential form of the limit. So the limit of an integer power p of a function is just the power of the limit of the function. So this is L, so L raised to p. So if the limit of f of x is 4, so we have this. If this is raised to 3, so you can just factor out the exponent 3. So if you want to use the factor out term, so this is limit of f of x is 4 based on the given. So we have 4 cubed, and 4 cubed is equal to 64. Now if the limit of f of x is 4 and we're given with this, the power is -2. So this is, again, applying the power theorem. This is equal to this. And limit of f of x is equal to 4. And 4 raised to -2 is equal to 1 over 4 squared. Okay, you take the reciprocal. And then 4 squared is equal to 16. So we have 1 over 16. Okay, so take note that if you have an exponent here, okay, then of course you can factor out the exponent. Okay, and therefore the result is the limit of the function raised to the exponent. This is the power theorem. And we have the radical theorem. So this is just I think a special case of the power theorem, because here P is, in general, it is an exponent, a power. Here, when we say radical, the exponent is just 1 over n. So it's still a power. 1 over n is a power. So this theorem states that if n is a positive integer, the limit of the nth root of a function is just the nth root of the limit of a function, provided that the nth root of the limit is a real number. So thus, it is important to keep in mind that if n is even, the limit of the theorem must be positive. So the limit of f of x equals 4. If this is true, then the square root. Limit of the square root is just the square root of the limit. So this is the limit of the nth root is equal to the nth root of the limit. Take note of that. Okay. So the limit of f of x equals 4. So the square root of 4 is 2. Okay, 2. Now, if the limit of f of x equals -4, then it is not possible to evaluate the limit of f of x because the square root of -4 does not exist. So you may practice these exercises. Thank you for listening.